In this video, we're going to take a deeper look into truth tables. We've already seen that they can be used to give the definition of our logical connectives, but we can also use truth tables for other things. We can classify propositions once we plug them into a truth table and see what their truth conditions are. We can also compare them to other propositions. In fact, truth tables can be extended to show whether certain arguments are valid or invalid. So that's why we want to take a look at truth tables. And the first thing that we should do is learn what the convention is in constructing truth tables. So let's turn to that. So let's start by considering a very simple case, not the case P. And let's say we want to make a truth table for this. We start by filling out our reference column. And the purpose of the reference column is to exhaust all the possible cases of the different types of truth combinations that can occur in the proposition that we're dealing with. So P can either be true or false. Truth is binary. It's 1, 0, good, bad, ugly, beautiful, true, false. So convention tells us that our first scenario at the very top of our column will be true. And our second row is representing those cases in which P ends up being false. So if P stands for instance, it's raining outside, then situation 1, case 1, is a situation in which you look outside and in fact it's raining, whereas situation 2 is when you look outside and it's not raining. Now, by having exhausted all the combinations, we can then see which situations in which the proposition it's not the case P is true in the cases in which it's false. Well, if I say it's not raining outside and it is raining outside, I'm wrong. That is, I've said something false. Although if I say it's not raining outside and in fact it's not raining outside, I'm correct. And so that's true. That was a pretty simple proposition. Let's take a look at one that's compound and has several different kinds of propositions in it instead of just one kind of proposition. So for instance, we might consider the proposition if P, then Q or R. And in constructing a truth table, we enter the proposition that we want to construct the truth table for on the right side, on the right column, and then the left side is going to be our reference column once again. As our propositions in kind that we come across left to right, so left to right, 1, 2, 3, we're going to enter them in the same order in our reference column. So we put P left to right, then Q, then R. Now remember, the purpose of our reference column is to exhaust all the possible combinations of truth that are available to us. So there's that situation in which R is true and the case in which it's false. But when we look at Q, we know that Q could be true when R is true, and we also know that Q could be true when R is false. But Q can also be false. So this doesn't yet exhaust the number of rows or situations that we need. So we need more lines, we need more rows. We need a row that accommodates the case for when Q is false and R is true. And we need a case in which Q is false and R is false. And now we can see that these two exhaust the cases in which Q can be true and Q can be false, and they line up with the two combinations for when R is true and false. So we're going to capture every single combination then. Well, when we add another proposition, we need to be able to do the same thing. We know there's going to be a case in which P is true and Q is true and R is true. We know there's a case in which P can be true, Q is true, and R is F. We know that there's got to be a case in which P is true, Q is false, and R is true. And there's got to be a case in which P is true, Q is false, and R is false. And that's going to, since we know that this exhausts the combinations for Q and R, we know that this exhausts the combinations for when P is true and then all these other combinations for Q and R. But now we're going to have to do the same thing for all the times that P is false, since truth is binary. So now if we just repeat this pattern, in all the cases in which P is false, then we'll get both of those combinations for when P is true and when P is false, and again we will have exhausted all the possible combinations. So we repeat the pattern for R, TF, TF, and we repeat the pattern in Q, TT, FF. Now there's nothing special about there just being three propositions in this case. If we add a fourth, we just continue the same pattern, and for the very same reasoning that I just gave, we'll know that it exhausted all of the truth combinations, and so on and so on and so on. So let me remove these color lines. In fact, it'll be easier to just kind of reconstruct this table. So we have the proposition real quick: if P, then Q or R. And we have P, Q, R in our reference column. And if we follow the same reasoning and the same pattern that I gave you, then once we figure out how many rows that we need, and given the reasoning that I gave, that will always be equal to 2, because truth is binary, there's two options, to the n power, where n is equal to the number of different kinds of propositions. So in our case, the number of rows that we're going to need, the number of lines that we're going to need, is 2 to the third power, because there's 1, 2, 3 different kinds of propositions. So 2 to the third power is equal to 8. So we know that in order to exhaust all combinations of truth value, we need 8 rows. We're going to need 8 lines. we can always get the same pattern that I was discussing if for P, for our most left proposition in our reference column, in this case P, if for the first half of the rows we give it T's, and then for the second half, so in this case that's 4 rows, and then in the second half we give F's. So if there were 4 propositions, 4 different kinds of propositions as opposed to 3, we would have 16 rows. The first 8 would be T, and the second 8 of rows would be F's. But since we only have 3, the first 4 are T's, and the last 4 are F's. Then we have that pattern. So instead of 4 T's, 4 F's, we go to 2 T's, because 2 is half of 4. We do 2 F's, because 2 is half, again, of 4. And then we repeat that until we exhaust all of the rows that we need. So we repeat that same pattern, TT, FF. And again, as we move to the right, we have it again. And half of 2, so there's 2. Now we're having this pattern. So half of 2 is 1. So we get the pattern TF, 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 and TF. And that gave us just the pattern that I was discussing earlier. And we know that that exhausts every single truth combination that's available to us. So notice there's another way that we can think about this. Instead of going left to right, you could go right to left, and notice that your most right column is always going to take the pattern TF, TF, TF for however many rows this formula tells us that we're going to need. And then you just double that pattern as you move to the left. So then instead of 1 T and 1 F, you get 2 T's, 2 F's. And then you continue that pattern until it fills up the number of rows that's needed. And then you just double the 2 T's to 4 and the 2 F's to 4 F's. And then if we had 4 propositions instead of 3, you get 8 T's, 8 F's as you move left, right? And then you get 16 and 16, and then you get 32 and 32, and your truth tables get very huge very quickly as we introduce more simple propositions. All right, so let's use this truth table and use this reference column to figure out the truth conditions for the proposition that we're concerned with, the compound proposition that we're concerned with. So the first thing that we need to do here is we need to figure out what our main operator is. And in this case, since our parentheses tell us to take this compound sentence as one unit, and this is a unit by itself, and our wedge is a binary connective, that is, it takes 2 sentences or 2 units in as values, this is going to be our main operator. It gives us the most general characteristic of what this sentence is. So most generally speaking, this proposition is a disjunction, and its left disjunct is a compound sentence that is material conditional, and its right disjunct is a simple proposition R. So in order to know the truth value of disjunction, we're going to need to know the truth value of R for each of the possible situations. And we need to know the truth value of this conditional, if P then Q, for each of the 8 possible situations, the 8 lines, the 8 rows. So in the case of R, it's really easy to determine what its truth conditions are because it's just given in our reference column. So it's T, F, TF, TF, TF. But in figuring out our left disjunct, if P then Q, we have to remember when conditionals are true and when they're false. And they're false in only one case. They're false in the case in which the antecedent is true. Antecedent is P in this case, the sentence that's to the left of the horseshoe, and our consequent is false, which is to the right of our horseshoe. So in this case, it's Q. Well, we see that in cases 3 and 4, our antecedent is true and our consequent is false. And that's the only case in which we get that pattern. So in all of the other cases, it's going to be true. So we get true, true, false, false, and the rest are going to be true. Now that we have the truth conditions for our left disjunct and the truth conditions for our right disjunct, we're in a position to determine the truth conditions for our main operator, which is a disjunction. And a disjunction is true just in case at least one of its disjuncts is true. So we look for any case in which both of the disjuncts is false. That occurs in the fourth row. And I can very quickly see that for the remainder of them, there's going to be at least one true disjunct because our conditionals are true in the remaining 4 situations. The left disjunct is true in the remaining 4 situations. So that gives us the truth condition for this compound sentence. It tells us that in situation 1, it's true. In situation 2, it's true. Situation 3, it's true. Situation 4, it's false. And in the remaining situations, it's true. And by situation, we mean these combinations of truth values. We can classify propositions into 3 categories. We can have tautologies, which are propositions that are necessarily true because they're logical truths. We can classify propositions as being self-contradictory, in which case they must be false, they're necessarily false, they're logical falsehoods. Or we can classify them as contingent propositions, in which case they're propositions that can be true or can be false depending on the circumstances in question. And we can use truth tables to be able to determine whether a proposition is a tautology, is self-contradictory, or is contingent. So let's do that. In the case of tautologies, we could take as an example, if P then P. So on the assumption of P, you're going to have P. Just intuitively, it's clear that this proposition is going to be true. But we can represent that with a truth table. So there's 2 cases to be worried about since we only have one proposition, and 2 to the 1 power is in fact 2. So we get 2 rows and TF. So in the first case, our antecedent is true and our consequent is true. There's only one case where a material conditional is false, and that's when the antecedent is true and the consequent is false. So this is true. In our second case, the antecedent is false and the consequent is false. Again, this isn't the case in which the antecedent is true and the consequent is false, so it's true. So no matter the circumstance that we consider, we find out that this sentence must be true. This statement must be true. And so it's a tautology. For self-contradictory, as an example, we can consider the sentence, not the case P and P. Again, since we only have one kind of proposition, namely P, we only need two rows because 2 to the first power is 2. And there's one case in which P turns out to be true, and there's a situation in which P turns out to be false. So, since this is a unary connective, the negation is a unary connective, this should be a tilde, that gets treated as a unit. This is a unit by itself, and our dot is a binary connective that is taking the left conjunct, that's a negation, and the right conjunct. So this is going to be our main operator. The dot's going to be our main operator, which means we have to figure out the truth of its conjuncts first. Our reference row gives us the truth conditions for the right conjunct, since it just is the right conjunct. So in the first case it's true, and in the second case it's false. In the next case, in the left conjunct, it's a negation, and it's negating the P, so we flip the truth values. Now, conjunction asserts that its conjuncts are all true. So it's true only in the case in which all the conjuncts are true. Well, we can see that our left conjunct is false in the first case, so the conjunction is false. And we see that the right conjunct is false in the second case, so it's false. And we can see that this sentence can never be true. It's always false. So it's a logical falsehood, or as we say, it's self-contradictory. So for a contingent sentence, we can take, again, as a pretty simple example, P and Q. So now we have P and Q that we have to worry about, since we have two kinds of propositions. So we need, since 2 to the second power is 4, we need 4 rows. It goes TF, TF, and TT, FF. The conjunction is true, just in case all of its conjuncts are true. So in our first case, where both P and Q are true, our conjunction is true. But we can see that in any of the other cases we look at, we'll have at least one of our conjuncts to be false, so we know the rest of them are going to be false. But since there is a case in which this proposition can be true and a case in which this proposition can be false, it's contingent. It's neither necessarily true or necessarily false. It depends on the situation. It depends on whether this is the situation that it obtains or whether one of these situations is what it obtains. We can also use our truth tables to compare different propositions, so two or more propositions. And there's various sorts of relationships that we might find obtained between them. So for instance, we'll take a look at the relationship of logical equivalence and the relationship of contradictories. And if we find out that the truth conditions of the propositions in question are the same, that is, they give the same truth value for each situation, they're logically equivalent. As far as their logical meaning goes, they say the same thing. If, on the other hand, for each of the situations, we find that they give opposing truth values, then they are contradictory. So let's take a look at an example that will flesh this out for us. So in the case of logical equivalence, we can consider the proposition if P then Q, together with if not the case Q, then not the case P. So we only have two propositions, two simple propositions, P and Q. So that means we're going to have 2 to the second power number of rows, which is 4. So TF, TF, T, T, F, F. And there's only one situation in which our material conditional is false. That's the situation in which its antecedent is true, but its consequent is false. That is the second situation. In all the other cases, the material conditional is true. Now, our main operator for our second sentence will be our conditional because it's binary. It has to take two sentences, and the sentence to its left is modified by a unary connective, so we have to treat it as a unit. And the sentence to its right is also one that is modified by the negation sign, a unary connective, so we have to treat it as a unit. So we have to figure out the truth values of those first before we can figure out the truth value of the horseshoe, the truth conditions of the horseshoe, and so that's why it's the main operator. Now looking at the reference column in Q, since we know that the negation just tells us to flip those truth values, we know that in situation the sentence will be false, second situation it's true, third situation is false, fourth situation is true. Again, looking at the negated P, we can look at our reference column to know what the truth values of P are for each situation, and our negation tells us that we need to flip that truth value. So then what we get is false, false, and true, true. Okay. So then our conditional is false in only one case. It's false in the case in which the antecedent is true and the consequent is false. So this negated Q is our antecedent, and this negated P is our consequent. And it's true and false in the second case. The antecedent is true and the consequent is false in the second case. So that's the time that we give a false. We look and we see that that's the only time that we get the antecedent as being true and the consequent false. So all the other cases get T as its value. It'll be true. And now we compare the main operator of our first proposition with the main operator of our second proposition, since that's what tells us the truth conditions of our statements. And we notice that they have the very same pattern, TFTT. And therefore, they are logically equivalent. They mean the same thing. All right, now let's look at a couple of propositions for the case of contradictories. So we'll look at if P then Q, and the other proposition that we'll look at is P and not the case Q. So we have our reference column. We have two kinds of propositions, P and Q. We're going to need 4 rows. And we fill out the reference row in the following way. And then we remember that our material conditional is false in one case, the case in when the antecedent is true and the consequent is false. That's case 2. In all of our other cases, it's going to end up being true. We can look at the reference column of Q to know what the negation of Q is going to be, since the negation just tells us to flip the truth values. So instead of TF, TF, we get FT, FT. And looking at the reference column, we can see that P, our other conjunct of the conjunction in our second proposition, takes the pattern TTFF. Well, the conjunction is true just in case both of our conjuncts are true. Well, we know that our right conjunct's false in this case, and we know it's false in our third case. It's going to be true in the second case since P is true and our negated Q is true. And it's going to be false in the fourth case because our left conjunct is going to be false. So then if we compare the truth values for each situation, we'll see that they're reversed, that they're opposing. So when the sentence, if P then Q is true, we see that it's false for P and not the case Q. And when if P then Q is false, P and not the case Q is true, and vice versa. So that's why these statements are contradictory. They always give the opposing truth value for any given situation. We can also use truth tables to determine whether propositions are consistent or inconsistent. Propositions are consistent just in case for a set of propositions we can find one line or one row on a truth table and where all the propositions come out to be true. That is, there's a situation, it's possible for all of those propositions to be true at the same time. they're inconsistent when such a line is lacking that can't be found on a truth table. So let's look at some examples to flesh this out for us. So for consistent propositions, let's take a look at P or Q as one proposition, and our other proposition will be P and Q. And so we're looking to see if there's at least one line in which these propositions both come out to be true. So we only have two kinds of propositions that we're worried about. So we're going to have 4 rows. We get the following pattern. To make sure that we exhaust all the possible truth combinations. Our first compound proposition is a disjunction, and it's true just in case at least one of our disjuncts is true. So examination of our first case shows that both of the disjuncts are true, so it's true. Second case, we see that the P is true, so at least one of the disjuncts is true. It's true. Third case, Q is true, so at least one of the disjuncts is true. But they're both false in the fourth case. And so our disjunction is false in that case. Now our other compound proposition is a conjunction, and it's true only in the case in which both of its conjuncts are true. So we look at the first case, both of the conjuncts are in fact true. P and Q are true in that case. So this is true. But a quick glance at the remaining cases shows that at least one of the conjuncts is going to be false, which means our conjunction is going to be false. But when checking for consistency, what we're going to be looking for is to see that there's at least one situation, that is one row, in which both of our propositions come out to be true. All we need is one. And in our first situation, we find it. When both P and Q are true, then our disjunction and our conjunction will be true. So they're consistent. Now let's think about a case in which the propositions are inconsistent. Let's look at the propositions P if and only if Q, and P and not Q. So we get our reference row, same pattern as the one before. Our biconditional is true just in case the left proposition and the right proposition share the same truth values. And they share the same truth values in 2 cases. The case in which they're both true and the case in which they're both false. Cases 2 and 3, their truth values differ. One's true and one's false. So we get false and false in that case. So our right proposition is a conjunction. The left conjunct is a simple proposition. The right conjunct is a compound proposition that's a negation. So we got to figure out the truth value of the negation first. It just flips over the truth value of Q in each situation. So instead of TF, TF we get FT. Conjunction is true, just in case all of its conjuncts are true. So we know that in our first case it'll be false since our right conjunct is false. We'll know that in the third case it's going to be false because our right conjunct is false. We know that since our left conjunct is false, in the fourth case will be false. But they're both true in this case. And when we look for a row in which all of them are true, all of our sentences are true, we have to look at the main operators. And we see in the first case, they're not all true because one of them is false. In the second case, they're not all true in that row because one of them is false. They're both false in the third case, and one of them is false in the fourth case. So for all the possible combinations, for all the possible cases that are available to us, there's not one in which both of our sentences here are true, and so it turns out that they are inconsistent.